Welcome back, students. We are going to continue the discussion we had in the previous video. In the previous video, we were trying to analyze a circuit that had all the three components: resistor, inductor, and also capacitor. This circuit is called as RLC circuit or LCR circuit. And what we said was that this source, alternating current source, this source will send a current through this circuit, alternating current in this circuit, and I can draw the phasor diagram for this. So I've drawn the phasor diagram. I said I've taken the instant at which I is 0. So at that instant I will be like this, and VR will be like this, because the voltage across the resistor will be hand in hand with the current. But VN will be like this, because the voltage across the inductor will lead that current by 90 degrees. Or you can say that the current lags the voltage across the inductor by 90 degrees. And VC is like this, because the current will lead this voltage by 90 degrees. Current in the capacitor, through the capacitor, will lead the voltage across the capacitor by 90 degrees, or I can say that the voltage lags the current by 90 degrees. So we have drawn this picture. And I told you that this is the net, right? So VL minus VC or VL plus VC, if you take that vectorially, and it will give you this resultant. And that in combination with this VR will give you this V, so which is actually your input voltage. So we did that in the previous video. Okay? So this is an AC current, and this is a AC voltage, and it will send an AC current, and this also will be an AC voltage. Okay, so I am going to write that. And we said that this V is equal to Vm sine omega t, and if this is so, the V is here, which means that the current is lagging this Vm by an angle phi, right? So my I is going to be equal to, say, Im sine omega t minus phi. So it is following the voltage. That is from the perspective of the voltage. You know, like you have chosen to represent, you've chosen to take this as a reference. The voltage is a reference. The time you consider as 0 is when V is equal to 0. So if you consider that, then you will have this equation, Vm sin omega t. When you say V is equal to Vm sin omega t, the time is measured with respect to the voltage. What I mean by that is, if when the voltage is 0, your time is 0. That's what you have taken. Okay? And if the voltage is 0 and this current would have some value. But think about it. It's just a reference. You can always change the reference. You see, you have your graphs like this. This is V. Okay, this is V. So your time is 0 here, and at that time, you know, the current can be like this. Okay, so this is voltage and this is current. Okay, so when voltage is 0, current will have some value, some negative value here. But who says that you must take only the voltage as a reference? I can always take the current as a reference, right? If you take the current as a reference, the same graph, if you take the current as a reference, then you see when current is 0, then voltage has some other number. You see, it's a positive number. So you can say that I am going to take the current as a reference point, and if the current is reference, then this voltage, the function will change. So if I take I as Im sine omega t, then my V will be for the same graph, Vm sine omega t plus phi, right? It's plus phi. So in both cases, you notice that the current is lagging the voltage by phi, or I can say that the voltage is leading the current by phi. It's the same thing. So if I take the voltage as a reference, then I will say that the current is lagging the voltage. If I take the current as a reference, then I will say the voltage is leading the current with the same angle. Okay. So if I can say this either way. That is what I'm trying to tell you. Both refer to the same graph. The first one I have taken the voltage as a reference, because the time I have chosen to be 0 is the time at which V will be 0 in this case. But in this case, the time I have chosen to be 0 is the time at which I will be 0, and if I is 0, then what is going to be the value of V? Here V is 0, what is going to be the value of I? So these two sets of equations refer to the same thing. Okay, so I just want to say that here. And now, if I take Im sin omega t as a reference, then clearly Vr will also be varying with this time, right? So in that case, this length, and say Vr is going to be with respect to time, it's going to be Vrm and then sine omega t, correct? So you will have a maximum Vr here. Okay. So if you take this, then that would be Vrm. The maximum value of this. And what about VL? So VL at any point in time is given by, say, it's also a sinusoidal function, so we're going to have V L M, and this should, VLM will lead the voltage, lead the current by 90 degrees, right? So it's going to be sine omega t plus pi by 2. It will lead the voltage, it will lead the current by 90 degrees. And what about Vc at any time t? That can be given by Vcm sine omega t minus pi by 2, because it's going to lag the current. I can write it this way. Or if I take this as a reference, Vm sin omega t as a reference, then everything will have, a plus phi added to it. And that's about it. Pretty much the same equations. So this is what it is. So this is Vrm, and this will be VLM, it's a maximum, and this will also be VCM, it's a maximum. So, and that's the that as the radius, it's going to make a circle, and this as radius, this will make a circle, and this as radius, it will make a circle. So we will have all these rotating vectors. Rotating vectors with this maximum, VLM, Vrm, Vm, and VCM. Okay, so this is what you will get here. Okay, now let me calculate Vm. So what is Vm? Vm is actually this vector addition of VL and VC, right? Which means that VC, this is going to be actually VLM minus VCM, right? Okay. So there, this is going to be VLM minus VCM. That's what you got here. And this is VR. So what is VM? So VM is equal to VRM squared plus VLM minus VCM squared, and then you get square root. I'll just keep it like this, VM squared. VM squared is equal to VRM squared plus VLM minus, this is L and this is C, M squared. Okay? Okay. So now, what is this basically? What is VRM? VRM is IRM into R, right? I or IM, I should say. IM into R will give me VRM squared. What is VN? That's going to be again IM into XL. Remember? The reactive, the inductive reactance, that is IMXL minus, it's going to be IM, this will be capacitive reactance, the whole square. Okay? So it is. So like I can take IM squared out, IM squared, take that out, then I get R squared plus XL minus XC the whole square. So that's going to be my VM squared. Now if I take the square root of this, then I am going to have VM is equal to IM into R squared plus XL minus XC whole squared. Okay? Square root. And what is my IM? IM then as VM divided by R squared plus XL minus XC whole squared. Okay, I want you to pay attention to this. So what is it? What does it remind you of? You see, if you have I is equal to V by R, right? So your IM is equal to VM by root of R squared plus XL minus XC whole squared, the square root. So, which means that this must have the units of R. That makes sense too, because we are squaring it, then you are also taking root. Okay? But this quantity is what we are going to call as Z. So I'll say that IM is equal to VM by Z, where Z is equal to square root of R squared plus XL minus XC whole squared. And I call this Z as impedance. Z is equal to square root of R squared plus XL minus XC the whole square, and this Z is called as impedance. Okay. Impedance is a combination of resistance and reactance. So together, this quantity is called as impedance of the circuit. This is resistance, this is the XL part of that, and this XL part of it is called as inductive reactance, and the XC part of it is called as the capacitive reactance, and these things together will be called as impedance. And the unit of impedance is also ohm. Why? You are squaring it and taking square root of it. So R squared, square root will be R again. So that would be, the unit of Z will be ohm. This is called as impedance. The impedance is given by this equation. Z is equal to R squared plus XL minus XC whole square root. Okay. See, XL can be greater or XC can be greater. But this can either be a positive number or a negative number, which is within the bracket. But when you square it, that will become a positive number. So we don't know whether XL is greater or XC is greater at any point in time. But like when you square that quantity, then it will become positive. So Z is equal to R squared plus XL minus XC squared. It is going to be a positive quantity, and you are going to take a square root of it. So that's how it is. It will never become a negative quantity. It's always positive. This is positive, this is positive. So you get a positive quantity. You get a real number, real value. Okay, so looking at this, you see I can represent this in terms of a triangle, right? So for example, if I can have R along this axis, and then this XL minus XC can be taken here. Okay, so this is going to be XL minus XC. Okay, so now this is going to be my Z. Right? I can represent it like that. So if you know R, if you know XL and XC, then I can do it like this. And see, I also have this phase angle phi. This is a phase angle with which the current was either leading or lagging the voltage. Is equal to, so I can take tan phi is equal to XL minus XC by R. Okay, yeah, but notice something here. I've chosen to have XL minus XC here, right? Okay. So tan phi is equal to XL minus XC by R. So if I know the value of tan phi, then I should be able to find phi. But think for a second. If the current lags the voltage, then it must be an inductive circuit, which means that if my voltage is written as V is equal to Vm sine omega t, then my current is going to be Vm sine omega t minus phi. Okay. So, this happens in the case of inductive circuit. The current will lag the voltage by an angle phi. Okay. But look at this equation. XL minus XC. If it is inductive, if the circuit is inductive, then the XL value will be greater and the XC value will be smaller. So I'll get a positive number. Then phi will be tan inverse of a positive number. That will also be a positive number. So it doesn't, even though it gives you the value of phi, it doesn't tell you whether the current lag is minus phi or plus phi now. Okay, it is like that now. where I should have got a minus 5 here, I actually am getting a plus 5 because I have chosen XL minus XC. Instead, if I choose XC minus XL, instead of this, if we choose XC minus XL, we say here, then I take this as XC minus XL, then this will be XC minus XL. Notice that when the circuit is net inductive, XL value will be greater than XC. So this will be a negative number. So tan inverse of 5, the tan inverse of this negative number will give me a negative 5. So that's what I get here. So it makes sense to define this like this. So I am going to rewrite the whole thing as Z is equal to R squared plus XC minus XL the whole squared out. What is the advantage? I mean, magnitude wise there is not going to be any advantage because if this is a positive number, this will be a negative number. But when you square it, that is positive. When you square it, this is also positive. So effectively you will get the same Z. But the advantage here is in calculating phi. So if it is a net inductive circuit, XL will be greater, XC will be smaller, I will get a negative number. So phi will be tan inverse of a negative number. I will get a negative angle, meaning the current is lagging the voltage. If I take the voltage as a reference, then current is lagging the voltage. This is what I will get. Suppose if it is net capacitive, the circuit, then XC will be greater, XL will be smaller, and tan phi will be a positive number, then phi will be a positive number again, meaning that the current will lead the voltage. So I will take care of this leading and lagging aspect of the angle phi with this definition. Instead of going for XL minus XC, if we go for XC minus XL, then the angle I get from this equation will also tell me whether the current is lagging or leading. If you get a negative number, the current is lagging the voltage. If you get a positive number, then the current is leading the voltage. So it's better to define it like this: XC minus XL instead of XL minus XC. Even though magnitude wise there is no difference. Okay, to summarize, say V in an LCR circuit, let's say V is equal to Vm sine omega t. This is the applied voltage. And in that circuit we have L and C and R. So what will happen is that you will have a current equation I, which is equal to Im and then sine omega t plus phi. Why am I using plus phi? That is because of this equation. Tan phi is equal to, remember, we defined it to be XC minus XL by R. Okay. So if it's an inductive circuit, this will become a negative number, then phi will become a negative number. So this will become a negative number. So automatically we will lag the current. Or if it is a capacitive circuit, then this will become positive number. Then phi will become tan inverse of the positive number, will become positive number. So this will become positive. The phi value will be positive. So even for capacitive circuit, the condition that I must lead the voltage will be satisfied. So there is one single equation which will work for both inductive and the net inductive and the net capacitive circuit, because we have defined tan phi like this. So if it is a net inductive circuit, this will give you a negative value which you can substitute there. And if it is a net capacitive circuit, this will give you a positive value which you can substitute again there. So this will be taken care of automatically. So this is the definition for the LCR circuit of voltage and current on the angle. So remember that it should be XC minus XL divided by R, not XL minus XC. If it is XL minus XC, then you need to convert that into a negative number. Okay. So XC minus XL, this holds good. If it is XL minus XC, then this must be negative. Write the omega t minus 5 to make all things work properly. So we just keep this in mind. Next, Z is equal to square root of R squared plus XC minus XL whole squared. This doesn't matter. This will become positive, whether XL minus XC or XC minus XL. So this is what we found. Then let's talk about the power in the LCR circuit. What power is it going to use? So we know that there is something called instantaneous power, and if you know the instantaneous power, you will be able to calculate the average power, right? So the instantaneous power P of t is equal to V of t multiplied by I of t. Anyway, V of t is this, I of t is this. So that is going to be Vm sine omega t multiplied by Im sine omega t plus 5. So we'll rearrange. So Vm Im sine omega t to this sine omega t plus 5, I'm going to expand it, sine a plus b. So this is going to be sine omega t into cos phi plus cos omega t into sine phi. So if I do that, that's going to be Vm Im sine squared omega t cos phi plus sine omega t cos omega t into sine phi, and this is equal to Vm Im, I should say small m, Vm Im, this would be sine squared omega t cos phi plus sine omega t cos omega t, sine a cos b, sine a cos a, so I can multiply this by 2, divide that by 2, so that will give me, if we multiply this by 2 and divide that by 2, then 2 sine a cos a, that would be sine 2a, so this would be sine 2 omega t and then sine phi by 2. Okay, so this is my instantaneous power. But what I'm interested in finding the average power, right? Okay, so average power would be 1 by t at power average, so equal to 1 by t integral p of t dt 0 to t. That's what it is. So that's going to be equal to, I'll take these two separately. So I'll get Vm Im, and cos phi, that's a constant. Phi will not change with time, right? It's a constant. So this is a constant, this is a constant, R is a constant. So phi will be a constant, so I'll take phi out. Cos phi, and now sine squared omega t. This is one function, right? Okay, so I'm going to integrate this, meaning that this would be 0 to t dt by t. So this part, and let's do the same thing for the second part. That will be Vm Im and sine phi by 2 integral 0 to t sine 2 omega t dt by t. Okay, so this is what we get for this thing. Let's see what's going to happen. You know this part, that's going to be half sine squared function, the integrated over the period divided by the time period would give you half. So that's going to be Vm Im cos phi. This will be half, right? We've done that before, so 1 by 2. Let's come here. This is going to be, what is sine 2 omega t dt? It is just sine function. It is sine squared function, sine function. We know the average value for the sine function is 0. So this term will become 0. So the entire term will become 0. So the average power is given by Vm Im cos phi by 2. Or I can do it this way. Vm by root 2 into Im by root 2 to cos phi. So average power is equal to Vm by root 2, that's V, RMS. Im by root 2, that's I, RMS, and cos phi. Okay? So note that when you combine all the things LC and R in a circuit, the average power is not just VRMS into IRMS. It's actually VRMS IRMS into cos phi. So this is called as cos phi. Cos phi is called as a power factor. Power factor. So if phi is very small, then the power factor will be very high. You know, like it will be close to 1. If phi is 0, then cos phi will be 1, so power factor is 1. If phi is not, it's close to pi by 2, then the power factor will be close to 0. Okay, so it will have very small power factor if phi is greater. If you have if phi is a smaller number, then you will have high power factor. So this cos phi is called as a power factor. Varies from 0 to 1. Okay, and this can also be written as, if I write this as a V as I into Z, we know that, right? We've done that already. So V is I into Z. So this is equal to V is I into Z, right? V is equal to I to Z. Yeah. So this we know. Or to be precise, Vm is equal to Vm by Z is Im, this is Z. So if we divide both sides by root 2, then I have Vm by root 2 into Z is equal to Im by root 2. So this will be, this is V RMS by Z is equal to I RMS. So V is equal to I Z. This is what I am Newton. So I'm going to put that here. So that would be PAV is going to be is IZ into I. So I squared Z cos phi. This is another equation. So P average can also be written. This is called as a power factor. Cos phi is the power factor. And now let's do example 7.8. A sinusoidal voltage of peak value 283 volts and frequency 50 Hz is applied to a series LCR circuit in which R is equal to 3 ohms, L is equal to 25.48 millihenries, and C is 796 microfarads. And find the impedance of the circuit. The phase difference between the voltage across the source and the current, the power dissipated in the circuit, and the power factor. So there are 4 things that they've asked you to find in this problem. So we'll do it now. So there is a sinusoidal voltage of peak value 283 volts and frequency 50 Hz is applied to a series LCR circuit. So the circuit is like this. So you have resistance, inductance and capacitance. This is R, L, this is C. So I goes through that, and then this is V. V is equal to Vm sine omega t. So what are the values given? First the peak voltage is given. Vm is 283 volts. So this is Vm is 283. Vm is 283 volts. And frequency is 50 Hz. Frequency is 50 Hz. And what else? Resistance is 3 ohms. R is equal to 3 ohms. And inductance is 25.48 millihenries. And what else? Capacitance is 796 microfarad. Capacitance is 796 microfarad. Okay. All these values are given. Okay, then they want you to find the impedance of the circuit. So what is the impedance of the circuit? Z. Z is the impedance. Impedance is equal to square root of R square plus XC minus XL the whole square. Okay. R value is given, so I need to find XC. So what is my XC? XC is 1 by omega C or 1 by 2 pi f C. So that is equal to 1 divided by 2 into 3.14 into 50 into 796 into 10 power minus 6. So if I put this all there, then I'm going to get this value. XC is equal to 4 ohms as per your textbook. I have not checked it. I trust that it is correct. So 4 ohms is what you get for your XC. And the next thing is I need to calculate XL. So XL is equal to omega L. So that is equal to 2 pi f into L. So that is equal to 2 into 3.14 into 50 into L is 25.48 into 10 power minus 3. Okay, so all that we put, then I am going to get this value. This is equal to 8 ohms. So XC is 4 ohms, XL is 8 ohms. So this is what I get. Okay, and I should be able to apply these values in this equation to get the impedance. So now a impedance Z is given by this expression R squared plus XC minus XL the whole square root. So this is equal to R squared is 3 squared. R is 3, so R squared is equal to 3, 9 plus XC is 4, XL is 8, so I'll get 4 minus 8 to the whole square. I'll just put here 3 squared, and that is going to give me 9 plus 4 minus 8 is minus 4 squared, it's going to be 16, so it's going to be 25, right? So if it is 25, then Z value is going to be equal to 5 ohms. That's the first part. Impedance is 5 ohms. Okay? And then what is that? The second part is the phase difference between the voltage across the source and the current. Okay? So the phase difference between the voltage and the current. So that is given by this expression tan phi, which is equal to XC minus XL. Note that carefully. It is XC minus XL, so that you will get the sign also correctly. So XC is 4 and then XL is 8, so divided by R is 3, so you get minus 4 by 3. So tan phi is minus 4 by 3, so phi is equal to tan inverse of minus 4 by 3, and that is equal to minus 53.1 degrees. Minus 53.1 degrees. So the negative sign, meaning the current is lagging the voltage. So this is a net inductive circuit, and that is clear from these values themselves. When you calculated XC, you found 4 ohms, and when you calculated XL, you found 8 ohms. So XL was greater than XC, so clearly this was a net inductive circuit. So that is why you are getting a negative angle, meaning that the current is lagging the voltage. So that is done. And what about the third part? The third part is the power dissipated in the circuit. Power dissipated, C. C. Average power is given by V I cos phi or I squared Z cos phi or V squared by Z into cos phi. Okay? So what can we do? I mean, they are given you the peak value, I can find VRMS, and I can also, if I divide it by Z, then I will get IRMS, and then I can take the cos value cos phi, and I can do all that stuff. Okay, but then it's going to be a little tedious, but I can do it smartly. How can I do it smartly? What is this Z cos phi? I want you to pay attention to that. How did we do this? So this was my R, and this was my XC minus XL, and this was my Z, and this was the phi. Okay, so Z cos phi is actually R. Z cos phi is actually R. So instead of this, I can just put P average is equal to I squared R. That shouldn't surprise you, because we have seen already that the average power dissipated in the inductor is 0. The average power dissipated in the capacitor is also 0. So any power loss must happen only in the resistor. So I squared R will be the only power loss possible in the circuit. I can ignore the inductance and capacitance. They may control the current. But they don't do much to the resistance. Okay? So this is what it is. Okay, so what is my I? I can be, so what is my Im first? Im is equal to Vm by Z. So this is IRMS is equal to Im by root 2, which is equal to Vm by root 2Z. So that would be, this is my I, correct? So if I do that, I is equal to Vm by root 2 into Z. So Vm is given 283. So 283 by root 2 into Z is 5 into 5. So if I do all this, then I get 40 amps as per your textbook. Okay, I get 40 amps. So if I know I, then I can find I squared R. So the power is equal to, average power is equal to I squared R, that is 40 squared into R is 3. So this is going to be equal to 4800 volts. So that is the power. And what is the last part? D. The last part D is power factor. Power factor is cos phi. And that is simply cos of minus 53.1 degree. Then I get 0.6 for that. So this is how you do the problem. And there are two things I want you to remember in this. One is the inductive nature of the circuit, which you can find from these values themselves. If XL is greater than XC, then this circuit is going to be net inductive. That is one point that you have to remember. And the other point that you need to remember is this. Z cos phi is actually R. The power loss will happen only in the resistor, whatever you connect. Ultimately, it's going to be I squared R. All these equations, different equations, will give you finally I squared R. These are the two things that you need to remember. These are the two takeaways from this problem. Hope this is clear to you.